Hi, and welcome to the introduction to my poster session on the MATP cohomology of unipotent groups. My name is Daniel, and this is made for the MCA Conference 2021. With that said, let's just get started quickly, and hopefully this will not be too long. So first, we'll start with introduction, then we'll talk about more specific subjects later. So first of all, what's the problem I'm looking at? So I have been looking, or originally I looked at this result by Grusser-Klune, and there was a part of the proof I couldn't really follow, and we ended up thinking that there might be a mistake in a part of the proof that uses a result by Grünenfelder, and we're trying to fix it. And we think we can fix it in the case when mu is 0, but then we ended up also showing more properties in that case, so we ended up kind of going in a different direction and proving something else. So let's talk about what the result we actually proved is then. So let's say we have P a prime that's big enough, which we'll talk about what that means later, and we have n some unipotent radical of a Borel subgroup of a split and connected reductive algebraic CP group, and we have a Lie algebra n, which is the Lie algebra of n restricted to Fp. Then we claim that NCP is a p-valued pro P group and thus a compact p-adic Lie group. We claim this multiplicative spectral sequence here, connecting the Lie algebra cohomology to the group cohomology, and we claim that this spectral sequence collapses at the first page, thus giving us certain isomorphisms which will be compatible with the cup product in a sense we'll talk more about later. And also I'll just quickly mention that if you want to think of an example, you can think of NCP being the group N, which is just the unipotent upper triangular matrices inside SLNCP, or specific, you can just take N to be 3 in this case, for the simplest example. Okay, also I'll just quickly mention that similar results to what we are interested in are already known in the case, for example, with CP coefficients. Ranchetti has this recent result connecting the cohomologies of groups with the cohomology of Lie algebras. And if you go further back, there's an old result for equi-p-valued group by Lazard. And there's also other results for compact real Lie groups. Okay, so that was like a brief introduction. Let's talk about then the setup for our specific problem and talk about why we get a p-adic Lie group. So our specific problem, we have a G, a split and connected reductive CP group, and then we fix a we fix a split maximal torus T of G. We fix a root system of G with respect to T. Then for each of our roots, we take a basis of the Lie algebra and some root subgroups, and with these we also then get some unique isomorphisms of group schemes associated with this basis in the following sense. And then we fix a basis of our root system, giving us positive and negative roots and a corresponding Borel. And then we take n to be the unipotent radical of our Borel corresponding to the negative roots. And we also consider the standard height function and a total ordering of the negative root. And this total ordering of the negative roots will just be used for when we do products, they will be with respect to this order. Okay, so first we will note that multiplication induces an isomorphism of schemes like this, allowing us to write n, which by definition is just NCP, as this product here, and that way of writing it allows us to introduce this function omega as here, and we use the convention then that omega 1 is infinity, and we want to show that this omega is actually a p-evaluation. So that's the first thing we do, prove that this is a p-evaluation. So I'll not talk too much about the proof, but the proof idea is to introduce some other subgroups, use some properties of those, which will give us most of the properties of being a pure relation. And then the last one you can get by long triple induction argument. That's very similar to something already done by Sabradi, and you just have to kind of change it slightly to fit our exact setting. So I'll skip all the details for now, and we can talk more about the details if anyone is interested in the poster session. Now, with what we just had, noting that N is a pro-P group, we get by a well-known result of Lazard that N is a compact p-adic Lie group. And that finishes the second part of this introduction. The third part is then to say that we get a spectral sequence. Before talking about the spectral sequence, I'll just note that the cohomologies we talk about, you can think of as just coming from the standard complexes when we talk about Lie algebra cohomology and group cohomology. Also for group cohomology, you can think of the continuous group cohomology too if you prefer, since we have pro-P groups. Now we note in our case, the Lie algebra will be graded by the height function. And in general, when you have a grading of a Lie algebra, you can transfer it to a grading of wedge products, which can then be transferred to a grading of the following Hom spaces by considering homogeneous maps. And one can check that this passes to a bigrading of the Lie algebra cohomology like this, which we'll use in the spectral sequence. Also, a well-known result due to Lazard will say that this graded N is actually a Lie algebra. So let's skip the details here and talk more about this also in the poster session if anyone is interested in these things. The main thing for now is that we have this Lie algebra G, which is the following tensor product, and we'll use that. And the reason we'll use that is there's this result by Sørensen that says we have this convergent multiplicative spectral sequence in a setting that's basically what we got to now in our case. And we also get by the spectral sequence being multiplicative, we get some compatibility with cup products, which we'll talk more about later in our specific case. So now let's talk about how we go from the Lie algebra G to the Lie algebra N, where we recall that N was the Lie algebra of N restricted to Fp. So first, we show this proposition, which Snyder has already done in some unpublished notes. And then we just simply tensor with Fp and get straightforward an isomorphism between G and N, which allows us to get this convergent multiplicative spectral sequence, connecting the Lie algebra cohomology of N with the group cohomology of N. So we have the spectral sequence we want, and it just remains to show that it collapses at the first page. So to do that, we can first use this result written down by Conrad, very similar to results well-known results by Chevrolet and de Mesure, that can allow us to transfer G, or from G, not transfer, like we can get to G, we can get an associated Chevrolet group, which I'll call GC. And we get corresponding unipotent radical of Sombrel there too, and a corresponding Lie algebra over the integers. And then, so the reason we want this is there are some results over the integers by Polo and Thiluin that we want to use. And they basically give these isomorphisms, we don't need the full details of what they do, but let's just say they give these isomorphisms as vector space isomorphisms, and we won't really care too much what the middle one here means. The main thing is just that VFP0 means just Fp concentrated in degree 0. So these isomorphisms allows us to say that the dimensions here of the different cohomologies are equal. And we want then to transfer this result over integers to something over Cp. So for this part, we can use an idea first described in Grosse-Klöne. And I'll skip a lot of the details again here, but basically we first connect the cohomology of Cp and C with Fp coefficients. by first transferring just from the homomorphism from C to CP to a map of cohomologies, and then noting that all these cohomology functors are the same, so those maps are bijective. And then by considering a nice filtration on NC with a parallel filtration on NCP, we can get by a result by Serre again that these induced cohomology maps are actually all isomorphisms. And thus, as before, the main thing we care about being dimensions, we get that the dimension of the cohomology of n with fp coefficients is the same as the dimension of the cohomology of the Lie algebra NC with fp coefficients. So we just need to transfer to Lie algebra n now, which is straightforward by looking at the chain complexes. We just straight away get that those cohomologies are isomorphic. So we get this equality of dimensions, which we can also write like this. And this equality here of dimensions allow us to conclude that the spectral sequence collapses at the first page. And that gives us these isomorphisms of graded cohomologies, where again, I'll not talk too much about the details of the grading and the group cohomology for now, and we can talk more about that in the poster session if anyone wants to. I'll just note also that this isomorphism is compatible with cup products coming from both the Lie algebra cohomology and group cohomology, in the sense that this diagram commutes. And then I'll stop for now and say thank you for following along with this introduction. I hope it will help you understanding what I have been working on, and hopefully I'll talk with some of you more at the poster session.